You have my timer, so it's.
Oh, I
I'm
will.
running
Running late.
late.
To be honest, a little late.
Ready to start? All right, so here we're talking about testing k-Monotonicity, subtitled Rise and Fall of Boolean Functions. So here we're working with sublinear time algorithms where we have lots of data or a very large complex object where we don't have a lot of time to scan the entire thing. And so we'd like to do something with this object at least, and hopefully not using too much time. So our goal here is to do something at least sublinear where we have query access to this object, and we'll use randomness along the way. We're thinking of queries as very expensive, and we want to make some sort of decision and hopefully get the right answer. There's some assumptions. So here we're in the standard egg model of property testing, where we're talking about classes of Boolean functions here. We have a notion of distance between two Boolean functions. It's just the fraction of points where they disagree, and the distance from a function to a set is just the minimum distance here. And our goal here is that we have to accept everything that's in the yoke here. We have to reject functions with high probability that are outside the egg completely. And if we're in the egg white, then you can like the egg white or not. The algorithm is allowed to do whichever. And our goal here is not necessarily running time, although we're not going to abuse this fact too much. It's more of an information theoretic problem. We want to minimize the query complexity as best as we can. We're talking about monotone functions, which have already been defined here, and we'll do this with a little bit more info here. If we have two comparable strings here where we flip just 1, 0 to a 1, the big bit's there are 4 possibilities for the function value on each of these 2 points. If we have a monotone function, we're not going to allow the last one, that if we change from a 0 to a 1, then we can't change the function value from 1 to a 0. So we're talking about monotone increasing functions, and you could generalize to monotone decreasing by slashing a different column instead. Equivalently, if we're talking about and, or, and not circuits, this is the same as the class that only uses and or gates. So you can compute it without not gates, but as we've seen already in this collection of talks, this isn't necessarily the smallest representation you would get, but this is another way to define the class of monotone functions, anything you could compute with a circuit that only uses and or gates. And so some examples, we have things like the majority function, and or themselves, k-clique, and several other examples. So trying to move on to what we're talking about here, let's go up one step just to 2 monotone functions for now. So here imagine that we have 3 sort of comparable things where we walk up changing a 0 to a 1 and then a different 0 to a 1. And so there would be 8 possibilities for a Boolean function here. And again, we're not going to allow the last one here, so we're not going to allow it to go from 1 to a 0 to a 1, similar to what we did with monotonicity here. And we can also think about the second column here being bad instead, but for this talk, we'll just think about the last thing here, these bad things starting with 1. So anytime you do not, if you have something like this, of course, you're not allowed this in a 2 monotone function. If you have something that violates either of these properties, things get a little bit different in the monotonicity versus even 2 monotonicity. That for monotonicity, if there is a violation like this, if you have something that's not monotone, you're guaranteed that there are 2 adjacent points like this that will certify that a function is not monotone. In the 2 monotone case, you're not guaranteed that this violation would be 3 consecutive points. I mean, definitely you could find an edge that has the top 2 violation for the bottom 2, but they might not all be neighbors. These violations might need to be very far apart, even in just 2 monotonicity.
Wait, that looks like a function is not even monotone, right? Or let alone not 2 monotone.
Right. So
what's the definition of 2 monotone?
These classes get more
restrictive.
Right. So 2 monotone functions are monotone, but not the other way around.
Okay.
Right.
And all right. What's the definition again?
So for a 2 monotone function, we're not allowed to see this pattern on any chain up the cube.
Okay.
If we look at the function values, we can't go from a 1 to a 0 to a 1.
Oh.
Similar
okay.
to for monotone, you can't go from a 1 to a 0.
Pattern.
Just that particular pattern.
Okay.
Right? For 2 monotone anyway.
Right.
We'll generalize this to k soon.
Oh, okay.
Any other questions? All right. So we can also talk about the circuit version here. We had a nice characterization for monotone functions. And for 2 monotone functions, it turns out there's the same kind of thing, which is due to Markov about 60 years ago, that you can actually compute a 2 monotone function with a circuit with and or gates and only at most 1 negation. You only need at most 1 negation for any 2 monotone function. And we'll generalize this one as well. So when we get to k-monotonicity, what we really mean by this is that there can be at most k changes on any chain. And so if we think about this in our violation framework, we'll say that we can't have a chain that starts at 1 and then goes to 0 to 1 to 0 where there are k plus 1 many points here so that there are k changes. This is not allowed at all. So we've already talked about circuits and things like that, so there is the natural generalization here, that Markov's theorem like we mentioned before. It says that you could compute any function like this with and OR gates and using at most logarithmic in k many negations. You can compute any k monotone function this way. Again, this number of negations is maybe off by plus or minus 1, but we won't worry about that. This has been studied recently by a paper with several authors, many of which are here, that any function like this can be written as the parity of k-monotone functions. So this paper, instead of looking at the testing problem, looks at the learning problem. I'm not going to define the learning problem too much here, since Liang just gave a beautiful talk about learning. So we'll just suffice to say that a learning algorithm produces a hypothesis H that's very close to an unknown function f, again assuming that it's k-monotone. And so for the learning here, they give an upper and a lower bound, that it can be done with random examples, with something that's exponential in this crazy thing here. It's a very rich class, so it does require a lot of random examples. And again, this is also polynomial in this sample complexity running time. And even if you're allowed membership queries, it still takes quite a few membership queries. So it's also very hard. So this exponent is not really that absurd. In fact, this has been known for about 20 years. In the case of monotone functions, you could just erase the k's or replace them with 1s. And these things are still true and have been known for a long time. Questions so far? Now we want to talk about the testing problem. So monotonicity testing has been studied for a long time. So just recently, we've got upper bounds that have been getting lower and lower, and now I guess should be a tilde on this, essentially using root D many queries. And this is a one-sided algorithm like we saw before that always accepts, and the queries are non-adaptive, so the further queries don't depend on anything that's already been done. There's a lower bound for this type that also essentially matches this, again, up to logarithmic factors. That's been around for a while. For some other models where you have two-sided error, where you don't have to accept every monotone function, you can get close to this if you allow adaptivity. The lower bounds are a little bit worse, but again, crawling up to square root D. So you can do a lot better than in the testing model than the learning model, which makes sense. So what do we talk about here? So our results are for k-monotonicity, and so we'll talk about the lower bound first. And so our lower bound looks like this, which is roughly something like d to the exponent k over 4. So something roughly like the dimension to the k. So this already says that if k is at least 3, then testing k-monotonicity is strictly harder than just testing plain old monotonicity. So it's already, got to be a little bit harder. And it gets really hard when k gets super constant, because then this bound becomes super polynomial. So what do we actually get? This seems like the right thing, although we don't quite get what we would like. We get this thing over here, which is close to maybe to what we would get if we just wanted to learn it and use previous results. This seems like kind of the right one, since every function is actually close to about root D monotone. So any lower bound that we get should degrade when k gets to close to root D, because then the answer is just yes, except, or you can actually do whatever you want. So this seems like kind of the right bound. And now this bound beats the testing bound, the learning bound anyway, so we're doing better than the learning lower bound that's already been given for k-monotonicity. So we're doing better than that. Now we can talk about the algorithm fairly quickly then. If we want to talk about this here, I've rewritten the bound a little bit differently with the d in the base rather than the log in the exponent. And so the theorem here is that if a function is far from being k-monotone, then we can find a whole bunch of disjoint witnesses that witness that this function is not k-monotone. So there are a bunch of these disjoint things, which is kind of like a matching, except that instead of pairs, we're matching k plus 1 tuples. And so our test really just says start at the bottom of the cube, walk your way up to the top. If you see a violation, then you're free to reject. If you don't see any violations after a while, then just say, okay, it's probably k-monotone, I'm just going to give up on this. Now, you might be thinking that that's not very much of an improvement, but maybe this will be a little bit better to see once we move to the hypergrid, where we talk a little bit about moving to the hypergrid instead. And so our main trick for the hypergrid is that we're going to use some sort of block coarsening. So we can think about an image as a function over a two-dimensional grid, where the pixel, the color of the pixel tells us the value of the function. And so then we can just block coarsen this function and divide this up into blocks, and then give the function a constant value on each of these blocks, which if you're looking at images corresponds to just pixelating an image here. So if we're talking about the hypergrid then, so instead of the Boolean cube, which would be 2 to the d, we're looking at n to the d. Doing well for time. We can do this with a query complexity that's independent of n. And so the main idea, like we said, was block coarsening, that the size of the blocks gets us to something where essentially we get a hypergrid where the n does not appear anymore. And one way we can do this is that we can essentially do agnostic learning over this block, and we already mentioned agnostic learning, where we can pretend we're trying to do as well as the best k-monotone function over this block coarsening. We get a query complexity that looks similar to what we've seen before. It's a tolerant tester, which in the egg model of testing means if you get close to the yolk, but you have a little bit of egg white on there, then that's still okay. That not only do we accept things that are exactly k-monotone, but we also accept things that are really close to k-monotone as well, and reject anything that's super far away. This can also work in a little bit different of a model then. We change our algorithm a little bit to handling real valued functions. But instead of talking about our distance being the number of disagreements, here that's the number of points where we have disagreement, we talk about having an average L1 error that is small. This already solves an open problem for tolerant testing of monotone functions over the hypergrid with respect to the L1 norm, which was an open problem from stock 14, I believe. And so this dependence might look really bad, but it seems like this might actually be required for many related problems. That even 2 monotonicity might live up to these problems like convexity and submodularity. Again, in the right models, if you change the model a little bit, then these problems get a little bit easier. I think there are some talks about this later in the conference. So it seems like that this really could be the right answer. One thing that also makes this seem like it might be the right answer is that if we look at the algorithms for testing monotonicity that already exist, which do give an exponential decrease going from something like 2 to the root d for learning down to root d for testing, what happens is that although the analysis of these algorithms really do use points that are very far away, that you're not just testing edges, sort of shotgunning edges at random to get down to root d, the analysis uses the fact that these edges exist, that there is a very local violation, because if you want to witness that you're far from monotone, you can always do it with 2 adjacent points. And even for 2 monotonicity, you might not necessarily get this. There might be a very large collection of 1s and a very large collection of 0s and so on, so that there aren't any really small violations. And so if you try to use some of these other techniques that work for monotonicity testing, they break down completely. So it seems like this really might be living in the exponential and root d regime. We have a couple of other techniques as well. One thing that I wanted to talk about, since it's kind of a cute application, is testing k-monotonicity on the line. And so if we want to talk about k-monotonicity on the line, if a one-sided non-adaptive algorithm, we have upper and lower bounds of k over epsilon. And one thing that's kind of cool is that if you are allowed 2-sided error, that you don't have to accept every k-monotone function, then the dependence on k goes away. And there's no lower bound that depends on k. You can get an algorithm that depends only on epsilon for its query complexity, which is pretty cool. Let's talk about these briefly since we have time for it. So on the line, one side we can test k-monotonicity with k over epsilon queries, and this is tight. The idea, like before, is we're going to do this block coarsening thing. So we have a Boolean function over the line, and we're going to block coarsen it in some way. And so the number of blocks is k over epsilon. If we started with a k-monotone function, then this coarsening function is also going to be k-monotone, and it's going to be very close to f. If f is k-monotone, it can only change so many times, and so that means that many of its blocks have to really be constant. And so then G will get the right answer most of the time, except on maybe these change points where things might get a little fishy, but there can't be too many of those kinds of things if f is really k-monotone. If f is far from k-monotone, and we block coarsen it, then either G itself is not k-monotone. If G is really k-monotone, but f was far from being, well then f has to be far from G. So what happens in this world? It's easy to check if G is not k-monotone because this function is just defined by k over epsilon bits. So you can just look at it. You can do whatever you want with it. You have as much time as you want. You can do whatever you like with this. Now, if it's epsilon far, you can try to check that f and g are far from each other. We have to be a little bit careful about this if we really want to get k over epsilon queries. And if you allow something like epsilon squareds in there, then it's very easy. We have to be a little bit careful here with the analysis that we essentially are going to do constant work per block to check things. If we try to check every block individually, that would be too expensive. But sort of amortized, we can do constant work per block. Again, we're trying to find k plus 1 blocks that are sort of weird, that have differences. So we have a witness for the violation of k-monotonicity. And so we really want to show that an epsilon fraction of the blocks are bad. And so if we have epsilon farness, then we're essentially doing constant work per block. But again, we have to be a little bit careful in the analysis that we can really do this. But the two-sided case, then, we can do something that's just polynomial in 1 over epsilon. So it's sort of just a random corollary. If you want to test n to the cube root of n monotonicity, you only need a constant number of queries that doesn't depend on n. Which is kind of surprising. It's a little bit less surprising that if you rename this class, then it's been studied for a while. So if you talk about this differently, these k-monotone functions are essentially testing union of intervals. These are union of interval functions. If we have a whole bunch of points, we might as well just pretend that we're working over the real interval, or the interval from 0 to 1 with real numbers. And then we really are looking at a union of interval functions. If we have a union of d intervals, that's essentially a 2D monotone function. We can also think about this in a surface area context, that if we're looking at this line, then the surface area is really just how many intervals we have. And this has been studied in several other papers, and I believe the best thing from other papers is 1 over epsilon to the 3.5. Although I don't think either of these papers thought about the one-sided case and didn't phrase it as k-monotonicity. But so why am I telling you about this if we have something where the query complexity is strictly worse? Well, the application in the way that we do it is fairly cute in that we reduce to a distribution testing problem. So we go away from Boolean functions and we work with just testing a distribution for a property. So we're going to do the same kind of block coarsening here. But what is the idea? We're going to think about this as a distribution somehow rather than as a Boolean function. And then when we think about it as a distribution, we're going to estimate its support size. So what do I really mean about this? I haven't really formally defined what this distribution even is. We're going to look at these intervals of constants here. So here I have a 5 monotone function, which is our coarsened function. We can break it up into 6 intervals that are constant if we take these intervals and make them as large as we can so that they're constant. We could define a distribution over 6 elements, and the probability mass on each is just the fraction of, that's the length of the interval over the length of the line. And then really testing k-monotonicity turns out just to be trying to figure out the support size of this distribution. And so how do we really do this? Well, we can do this as long as we can simulate a couple things. So we can estimate the support size of this distribution with a number of queries that does not depend on k or n or anything like that, as long as we have oracles for 2 things. One, we can randomly sample from this distribution. And secondly, we can get the probability mass of anything that we sample. So how do we actually do these things? Well, if we pick a random point on the line, that gives us a uniformly random block. And if we look at the interval that contains that block, then that gives us a sample according to this distribution. Now, we have to be really careful about this because we don't necessarily get the name of the interval. If we sample this thing here, we don't get 5th interval back. We just sort of we know that we're sort of working with the 5th interval, but we don't get the number 5 or anything like that. If we really wanted that, then we would have to query everything to the left, which would be far too expensive. So we have to work with this without actually knowing the names of our intervals. Seems kind of silly maybe that we can actually do this. How do we get the probability mass? Well, all we can do is just walk in the left and right directions and see how long the interval is. If we query, say, this guy here, say, oh, there's nothing to the left, there's one extra thing, or there's nothing to the right, there's one extra thing to the left, so this probability mass is 2 out of 10. We have to be careful again that we don't walk too far, because if we were working with a constant function, then we would be walking across the entire line, which would again be way too expensive. So at some point we say, okay, we've walked long enough, we're going to give up, sit down, and say this interval is just super big. which turns out to not affect the analysis too much. And then once we have this, we can use the support size estimator to get the support size up to a multiplicative factor, and this is enough to test whether or not we're close or far from monotonicity, or k-monotonicity, sorry. So what kind of questions does this leave open then? Again, our lower bound looks something like d to the k. So we'd like, is there really a poly d to the k test for the hypercube? This maybe seems like the right answer, but it could also be exponential in root d like we saw. We'd like to get two-sided lower bounds that have k's in them for other things. We can sort of steal monotonicity lower bounds and give k-monotonicity lower bounds, which seems like it should be obvious, and it is morally true, but it's not completely obvious that we can. We have our nice line case, but does that extend to the grid? I'd like to get a significantly better test for the hypergrid, but again, we're sort of blocked by the cube for the moment. And what is sort of the right way to generalize union of intervals to higher dimensions, where maybe something like distribution testing would be an effective way to approach this problem?
I think we're way over time, so let's take the questions to the break. And maybe, can we have, Chris is Bobby, can we have a break? What's the...
Okay, so is this...
yeah.
Right. So, okay, so what we promised you for ITCS is that the room would be full, not that we have no time, okay? So I think that we are way behind, so, you know, Bobby is going to chair the next session. Why don't we have a 10-minute break and start the last session of the